This is Chapter 14, Section 3, and today's lesson, kind of wrapping up just our basics on acids and bases. We're going to look at conjugate acids and bases, neutralization reactions, and acid rain and the effects of that. So starting off, conjugate acids and bases. Conjugate base. So according to Bronsted-Lowry, when we're talking conjugate bases and conjugate acids, after Bronsted-Lowry acid gives up a proton, it becomes the conjugate base of that acid. So as we look at this, we've got our acid right here, hydrofluoric acid, and once it gives its hydrogen over to water to become the hydronium ion, what's left is F minus, and this ion becomes the conjugate base. So the pair, you have an acid that is paired up with the conjugate base, or CB. And just the opposite here, you do have two acid-base pairs known as your conjugate acid-base pair. You've got your acid one, which is hydrofluoric acid, again, giving up to your base, or F minus. So you have your acid conjugate base here, and then just the opposite here, our base water, which has accepted the proton. This will be our conjugate acid that is paired with our base. I will come back to this particular neutralization reaction a little bit later in this section, and we will go over it in detail what's going on in neutralization. So the stronger an acid is, the weaker its conjugate base, and the stronger a base, the weaker its conjugate acid. So you've got your 7 strong acids that we've looked at. Hydrochloric acid is a strong acid, and then water is our base here. So since hydrochloric acid is a strong acid, the conjugate base that it produces is going to be, I did that to the wrong one, HCl, the conjugate base, to the chloride ion. That will be a weak base. So make sure you know the difference between strong acids, strong bases, and then the relative strength of the different conjugates that they do. And I'll show you a chart here in just a moment. So we've got 2 examples here. HClO4, which is perchloric acid, it is going to be a strong acid. So its conjugate base, after it loses the hydrogen ion, that is your perchlorate ion, is going to be a weak base. And of the same regard, in this particular one, you've got your water, which is a stronger base, picking up a proton, and that will be a weaker conjugate acid. So again, conjugate base here, conjugate acid here from the acid-base pair. In the reaction that is right below this, we've got acetic acid, which is a weak acid. Whenever it donates its proton, and you get the acetate ion, that is a stronger base. And then, again, conjugate base there. Water, in this particular case, is going to be a weaker base since it's paired with a weak acid. And once it accepts that proton, you get a stronger conjugate acid in the hydronium ion. In this one right here, the reaction to the left is considered to be more favorable, and I am highlighting the arrow pointing for it. So that was a reversible reaction. Now, this chart right here, I would say you're going to need this particular chart for any homework that you do. So get some of it written down within your notes. If you are at school, it's going to be on page 485 in your book, but you are going to need this. I'll try to get a copy for those that are in class. But as I look at this right here, notice that you've got, oh no, I went back and looked. It is page 467 in the book. Again, if you're in class, I will give you a copy of this. But as you're looking at this, And we're highlighting some things here. Right along the left, you can see on the conjugate acid side of things, the higher up you go, you have an increase in acid strength. So your hydroiodic acid is going to be stronger. And then as far as a conjugate acid, moving all the way down to hydrogen at the bottom. And then on the other side of this, notice the arrow is in the opposite direction. So you have an increase in base strength as you move down the conjugate base group. So at the bottom, you have the hydride ion, but notice your carbonate phosphate ions, hydroxide ion are there at the stronger end of this. And then up near the top, you can see that, look, your HI, once it goes over to here and becomes a conjugate base, if it lost the hydrogen, it's now a weak conjugate base. So I have introduced you to this word previously in the chapter amphoteric, and it's a species that can act as an acid or a base. And we have been talking about water acting as an acid or a base. You know that it's right there in the middle of the pH scale, but depending on what it's paired with, it will act as the opposite of whatever the reactant is that it's paired with. So in this example, if I have sulfuric acid to start with, which obviously is an acid, then water will act as a base. And you have your acid producing your conjugate base over here, and water acting as a base will produce its conjugate acid of the hydronium ion. In this bottom example, ammonia is a weak base. So you've got water acting as an acid here. So if I look at my acid-base pairs, so this is my base, my acid, this is my conjugate acid, which ammonia accepts the proton. And then we've got our conjugate base over here, where water acting as an acid loses a hydrogen ion to produce your conjugate base. So a hydroxyl group, or known as the bonded OH group in your acid, if it contains this hydroxyl group, it can be acidic or amphoteric, and the behavior of the compound is affected by the number of oxygen atoms bonded to this hydroxyl group. We're going to look at an example of this and show you the behavior as far as how many oxygens you have. So in this one right here, you've seen I call it the chloride family, but you've seen it as far as what it is bonded to and the number of oxygens if we're thinking polyatomic ions. So hypochlorous acid, all the way up, chlorous, chloric, perchloric acid. You can see the number of different oxygens that you have. So this is HClO, HClO2, HClO3, and HClO4, and the acidity increases off of that hydroxyl group, OH here. In each of these cases, the more oxygens you add, the more acidic that particular compound will be, and we know that the perchloric and chloric acids are both considered to be strong acids. So make sure you know this correlation. Okay, so back to neutralization reactions. Neutralization is in a reaction of hydronium and hydroxide ions that form water molecules. And then a salt is any ionic compound that has a cation from a base and an anion from an acid. So in this one right here, we have hydrochloric acid and sodium hydroxide. That's a strong acid and a strong base, creating, through a double replacement reaction, salt and water. Salt and water. So we will break down this neutralization reaction. So I am going back to this picture that you saw earlier, and we're going to have a hydrochloric acid or sodium hydroxide, and you can see that the hydrochloric acid starting with in this one, it is breaking it down into the hydrogen ion, the chloride ion, and hydrogen attaches itself to water to give you the hydronium ion. And in the other one, where we had our sodium hydroxide, again being a strong base, is going to break down into the sodium and hydroxide ions within water. So what is your resulting reaction going to be? We said that it forms salt and water, NaCl, because the Na and the Cl are going to get together. And it says, well, if you evaporate whatever is in this mixture, you will get salt, and then water will evaporate off. But let's go through the full neutralization reaction. So whenever we put our hydrochloric acid into water, you are going to have ionization that takes place, and we create the hydronium ion and chloride ions in solution. So you can put aqueous back here behind all of these ions. And then our sodium hydroxide, and you've seen these top two reactions in the previous section. Sodium hydroxide will break down into the sodium ion and hydroxide ions, again, both of them in aqueous solution. And when you add these two together, you get HCl, sodium hydroxide, creating their salt, NaCl, and water. Now, if we were to look at equal concentrations and equal volumes of this, so again, equal concentrations and equal volumes of both of our reactants, let's show what our overall ionic equation would be. So we would have H3O plus. And again, when I break this particular one down, I'm just trying to change my colors here. The hydrogen ion that is coming off of this will attach itself to water to give us the hydronium ion. So I don't want you to be confused over, wait, when I split H and Cl, where's just H plus the hydrogen ion at? But it will attach itself to water. And then the sodium hydroxide will break apart too. And again, we've got the sodium and the chlorine there, and just to balance everything out, 2 water molecules on the end, because I made that into the hydronium ion instead of just leaving it the hydrogen ion. So if I were to look at the net ionic equation, I would end up having our H3O plus, OH minus, and then the 2 waters over here. Again, this is for a neutralization reaction, and our NaCl can be evaporated out, the salt that is left over there. The resulting solution is going to be more neutral than the acid or base that created it. So again, we do have a strong acid, a strong base. This is the, I'm writing these in the wrong spot. So we have a strong acid, a strong base. They will create a salt and water for the neutralization reactions. And again, the resulting solution will be more neutral than the acid or base. The salt itself can be pulled out, and then you've got your water, which is in general considered to be a neutral compound. Okay, switching gears again, moving on to acid rain. You're going to want to make sure you get all of this down about acid rain and weathering. But it's giving you several different gases that are typically made during industrial processes that do dissolve in atmospheric water, so dissolve in the atmosphere to give us acidic solutions. So you got your nitrogen monoxide, nitrogen dioxide, carbon dioxide, sulfur trioxide. And in the example, they're taking the sulfur trioxide, reacting it with water that's in the air, and that gives you sulfuric acid. This is very acidic rain known as acid rain, which can erode statues and affect other ecosystems. So again, this is just a picture of what acid rain can do. So that particular line made out of marble or whatever it is made out of there is going to be pitted. And then under chemical weathering, again, I can't get the visual concept to play, so I'm going to highlight everything that was in the visual concept. So our first one, we've got several different ones. So we've got dissolution that can happen as a form of weathering, oxidation, hydration, dehydration, and hydrolysis. I will verbally give you what each of these type of weatherings do. Please make sure you write them down. I am not going to write them out though for me. For dissolution, we do have multiple ions that are typically involved. So with these particular ions, each of these can leach out of rocks when water is around. So they can leach out of rocks whenever water is around. Your oxidation forms iron oxides. So oxidation forms iron oxides. Hydration is when water is squeezed into a compound. So water is squeezed into a compound. And dehydration is when water is forcibly removed from a compound. So dehydration is when water is forcibly removed from a compound. And then hydrolysis. You have your hydrogen ion and hydroxide ion that form water. Hydrogen ion and hydroxide ion that form water. This is integrated into a compound. So integrated into a compound, and permeability increases. Permeability increases, and it exposes more rocks to chemicals. So again, your hydrogen and hydroxide ions form water, which is integrated into a compound. This causes the permeability to increase and exposes more rock to chemicals. These two right here, your hydration and your dehydration, they do create zones of weakness. So those two create zones of weakness.